Hello everyone, my name is Victor Basu and I am a data scientist at Lumik. Right now I would be demonstrating an architecture where we would be deploying a Hugging Face transformer model on AWS SageMaker and publish a model performance evaluation dashboard on AWS Quicksight for our deployed model and also exploratory data analysis or EDA dashboard over the entire dataset on AWS QuickSight. So our first step would be to deploy a Hugging Face transformer model on AWS SageMaker. So AWS SageMaker comes with Hugging Face deep learning containers, which really makes it easier to train and deploy transformer-based model on for production via AWS SageMaker. So the problem statement that we have picked to support our architecture is a diagnostic prediction problem, which is basically a biomedical NLP problem that aims to solve, like the medical prescriptions and different diagnostic reports generated by doctors and pharmaceuticals and hospitals to classify those text reports and analyze and categorize them to a diagnostic procedure, like whether a patient need to be diagnosed within a certain category or what kind of a disease a patient is suffering from uh, with respect to the data or the prescription or the reports provided by the doctors or the hospitals. So that would be our problem statement. So first we would be installing the SageMaker library, the transformer, which is the Hugging Face transformer library and dataset for S3. Next, we would be importing importing the necessary libraries here. Our next step would be to get the permission, like whether the bucket permission and the AWS SageMaker session permissions. Uh, then we would be reading our dataset from our S3 bucket. So our dataset is available at the dataset directory here, and we would be reading our dataset from the bucket directory. And here is some, the nan values evaluation, like how many nan values are there for transcription. So transcription would be our main text that we would be classifying, as I mentioned before, like the medical report or the prescription prescribed by a doctor. So that is our transcription, and medical specialty is the category that we need to classify, like what kind of medical condition the patient is in, or what kind of diagnostic to be done over with respect to the reports provided. We need to classify them. So we would be doing some pre-processing. So the main step, or like the major pre-processing step here, explains that like our target class or the medical specialty class is a 40 class classification, like a 40 class, categorical problem. So we need to bring down those 40 to some extent, like to 20 or like 30. So that's why we are doing a feature engineering here to actually drop down, or like, like concise the entire data set to some limited categories, so that it becomes easier for our model to predict, and we would be getting a better performing model with this pre-processing step. So after we have done the feature engineering here, we have added it to our field as medical specialty subgroup, where we are actually subgrouped the medical specialty category. Now next, as you can see, this is the original category, the count here it's 40, like too many categories for a model to predict, and next step we would be reducing it to like 23. So one can go with the medical specialty subgrouping as the target classification also, but to challenge our model, like how much a model can perform when it's reduced to 23. So to challenge that, I would be using this updated, a target group that basically holds the reduced 23 class classification. So our next step would be to store the pre-processed data to S3, and we would be using the pre-processed data to provide to provide a EDA dashboard, publish it, and our next step is to pre-process the text, as we are doing some basic NLP pre-processing, like removing the bad words which are like 09 A to Z and all of this. So even after, we have downsized the number of classes, it's still an imbalanced, like the classes are imbalanced. So to tackle that, we would be using class weights. These weights would be added to our custom model trainer here, custom model trainer, and we would be adding our class weights to the loss function to actually, to leverage each class equally, and we have a proper estimation of the loss, and so that our model also performs better. And so we would be using this later on, right now I have only estimated it, but you can directly use it at your train.py file, it's just exactly the same. So I have splitted the data set here and used data a load data set, which is actually for loading it to S3. And before loading it to S3, I have actually tokenized using distillbird base uncased. So after tokenization, like while tokenization, I am actually keeping padding true and truncation true, which actually means that the max length of each text would be equal to 215, which is the max length accepted by the pre-trained model. You can also do a downstreaming task to actually increase this length and train your model. That would be a better approach to have a, higher accurate, or a good performing model. So we are tokenizing the training and test dataset, finally uploading the training and test dataset to S3. So our model gets saved here. Sorry, the training and test dataset gets saved here. Dataset info, like the training one, and the test dataset also here. And also previously, as I mentioned, the pre-processed data is stored, so it's stored in here, the preprocess.csv. So right now our next step would be to create a SageMaker estimator to train our model. So this is the train.py file, which actually accepts the different hyperparameter. And the change that we have done here is creating a custom trainer. Having custom trainer gives you the leverage of adding the class weights here, in our case especially, so that the loss function could be evaluated by giving equal leverage to each of the class, and you can have a more accurately performing model, rather than one class getting more leverage than the other. So it's really beneficial to in such an imbalanced classification problem, where we actually defined a custom loss over a custom custom trainer model. So yeah, so we are using a transformers, like auto model from sequence classification trainer and training augmentation. As model also, we are accepting like the and distillbird based uncased model, which we have also used for tokenization, as I have shown before. So yeah, we would be downloading or like initializing the model, and then doing the training augmentation, and finally more trainer.train, which would be training our custom trainer, training it, and then finally evaluating and saving the model to our S3 bucket. So we are initializing the hyperparameters here. For we would be training for 10 epochs. Batch size for training is 64 and for evaluation it's 32. Learning rate 3 to the power minus 5. So we are initializing the Hugging Face estimator here. Here output path signifies that our model would be stored in the signified output path. The let me show you, like here model. Here as you can see the model is stored, and in if I go out to output, here you can see the output dot start dot gz actually stores the finally trained model, which you could actually use for redeploying your model, like after like evaluation, or if you want to terminate the endpoint right now, and you want to redeploy your trained model after certain period, you can use the model from there and redeploy it from here. And next we would be like training our model by doing a estimator dot fit our training path. So yeah, our model would train after that. So we are using an instant type of Nlp 2x large, which is actually quite good for training a transformer based model. It's actually $3 per hour, and the model takes only like 15 to 20 minutes to train for 10 epochs, which I think is a pretty good trade off in our case. If you want to go for BERT or Robert model, better have a uh, instance with higher GPU and higher CPU memory. That would give you a bigger advantage. Otherwise, you are going to get GPU, memory out of memory error or something like that. So you would be facing such issues if you do not ship for a higher instance for BERT and Robert models. So we would be training it. Training would like go for, like as I mentioned, like 10 or like 15 minutes. After the training, the model gets stored finally, like saves the checkpoint, and finally dumps it to the S3 bucket that we have mentioned. And yeah, it bills only for the like that training duration, and then it completes. Like you won't be charged after that. So next we would be doing after training is to deploy our endpoint. So we would be deploying it on a MLT2 medium instance, which is basically quite good, as for deploying it takes like within 1 second it provides a prediction. I think it's pretty good. But if you have something like you want to provide prediction within milliseconds, I would suggest you to go for a higher instance to have such faster predictions over your deployed endpoint. So at this step, we are actually deploying the endpoint. And as you can see, the deployed endpoint, we provide input and it provides the prediction. In here, at this step, we are actually evaluating our model's prediction over the test cases, or the uh, evaluation cases uh, in. So we would be providing the model the inputs from our evaluation set and storing the prediction and score likewise for each of the cases. So as you can see, finally we would be having a prediction, model prediction, and the score for each of these text or the evaluation test cases. And the score basically signifies the confidence for a model to predict a particular class, like how much confident it is to predict that class, and like kind of the confidence of the model to predict that class. So our next step is to upload this this updated data frame or the evaluation data frame to S3. This would be later used for like building the model predict a model performance evaluation dashboard, where we would be estimating the model's performance over the deployed model. So it's basically stored in the pre-process segment, pre-processed in eval. The model performance CSV is stored here. So our first step, model training and model deployment, is complete. we have successfully deployed a Hugging Face SageMaker, Hugging Face transformer model on SageMaker. Our next step would be to deploy a QuickSight dashboard for model performance evaluation, like to analyze like how the model has performed. For a 30 class, for a let me just check one more time. For a 23 class classification problem, I would say like 29.6, which is almost 30. For 10 epochs is quite not good, but quite good also. Like, yeah, like for a 36 class, sorry, for a 23 class classification problem, it does take some time to converge. Like the training and evaluation graph does take some time to converge. So yeah, I think it's okay for a demonstration purpose, but better have a higher accuracy when you would be deploying it on your end. So how did we, like come up with the count for correctness, then accuracy, then precision, macro, average, sensitivity, then F1 score? Because QuickSight doesn't provide any matrices for model evaluation. It just provides, the graphs that you want to deploy, or the charts that you want to deploy, uh, and the calculated field. So we would be writing a calculated field to evaluate each of the we would be writing a calculated field to provide an estimation of our model performance. So for correctness, our calculated field would, let me just undo it, sorry. So for correctness, our model would, for a correctness, our calculated field would look like this. Like if prediction equals to target, it's correct, otherwise wrong. So that's how we are going to get an estimate how many of our predictions are correct over evaluation set and how many are wrong. For accuracy, our corrected calculated field would look like this. Count if correctness, comma correctness equals to correct divided by count of correctness, which is actually, like total true positive plus false positive divided by total number of samples into 100, which is actually how we calculate accuracy. Now for precision also we would be following the same, like the rule, like how precision is calculated, like true positive divided by true positive plus false positive. We would be creating such a formula. Oh no, I have removed again. So yeah, yeah. So like we have done for prediction, where prediction equals to 0 and target equals to 0, divided by count if prediction, where prediction equals to 0. So we are actually calculating precision for each of the classes and doing a summation, and then doing an average, like dividing it by 23 into 100, which is like macro averaging. You can also do weighted averaging, which is providing weights of the classes or the significant classes, multiplying it with significant classes, the weights, and then providing an estimation. You can also go with that, and also you can go with micro averaging also. So yeah, so that this is how we would be providing the precision score. uh, Currently I don't know how to like add a for loop in like QuickSight. Yeah, like having a for loop would actually, like clean up this much of code. So like it would be a better, like if you know how to use a for loop, use a for loop, then like it would be more cleaner way to write the code. And similarly recall, which is actually true positive divided by true positive plus false negative. The same we have done here for each class, like for prediction equals to 0 and target equals to 0, and count if target, where target equals to 0. Like this we have calculated recall for each of the classes and did a macro average of it and published the score. Similarly for F1 score also, it's twice, 2 into like precision into recall divided by recall plus precision, which is recall and precision are our previously calculated field, and we are providing a macro average of F1 score. So one of The scope of or scope of improvement that I would like to add is like having a chart that would describe the precision of each of the classes, and recall for each of the classes and the F1 score for each of the classes. Like adding such a graph would be really like improve this dashboard to analyze each class and how each class has been reacting, or like how has understood each of these classes. So it would be a better analysis in that case. So, and also like adding a confusion matrix for each classes, like the false negative, the true negative, adding a confusion matrix would be really helpful, and improve the dashboard understanding and visualization if we had it. So these two are my points on like having a scope of improvement for this dashboard. And along with this, precision, macro average, recall, and accuracy, we have actually shown the score by model prediction, and the average of standard deviation of score by model prediction, and average of score by model prediction. We are doing average of score because to signify how each of the class, a model is predicting each of the class with what confidence, or the or like with what confidence each of the class are being predicted by the model on an average. So that we are trying to establish here. Same goes for stress standard deviation also, like how much standard deviation is created within the score for each of these classes. So that was the analysis, and the distribution of target versus a predicted feature versus predicted target feature is like distribution of uh, target variable over the validation data set, and our models distribution, like distribution generated by our models prediction over the validation data set. So this is how the entire dashboard is created, and it could be improved with the scopes of improvement that I have mentioned. On EDA also, like EDA, there is nothing much about like adding a calculated field. It's the distribution that we are trying to show here, the medical specialty, the distribution of like how many of the classes are there and what's their count. Like having an analysis of such can help you understand that whether a class has increased or not, or like any class has been added or not, so that you need to retrain your model. And this is the distribution of workload. This also helps you to understand like currently surgery, the amount of class for surgery is at maximum, but later on any of these could increase, like radiology could increase. So analyzing that would help you to retrain and understand the data and model better. And this is the relation between medical specialty subgroup and medical target class subgroup, which is actually here. Like I mentioned that we are doing a pre-processing. We are bringing down it into some subgroups so that our model could have a better understanding and for better prediction. So that we have visualized here, like the subgrouping, entire subgrouping that we have done, how it is connected to each of the main classes. And finally the subgrouping that we have actually used for training our model, like others we have mentioned here, like what we would be any category less than 50 would be considered as other than that all we would be considering to train our model. So this category, as I mentioned previously, this category or this medical specialty subgroup could also be used to train our model and have a better more model prediction, or a better performing model. But just to like challenge our models or the transformer model, I've used this subgrouping to just challenge it, that how much it is able to like tackle, or like put up a performance over to a 23 classification problem, which is like quite a big challenge, like to understand the pattern within the data to classify within 23 classes. Now, next would be to top 100, like transcription context. Transcription, which I mentioned, the like the prescription or the medical report generated by a pharmacy, hospital, or a doctor. And here is the like word count or sorry, the word cloud for our transcription context, which can give you an understanding of like how much the like the medical analogy or the evaluation of doctors or what kind of transcription are on priority in upcoming days. It would help you to analyze such scenarios. So so this was our entire architecture. Like we successfully deployed QuickSight dashboard for model performance evaluation and EDA. And as I mentioned that it is really helpful when you want to have a server side dashboard that could monitor your model that is performing on the client side. And that was it for today. And this entire code is available on GitHub. Like I have mentioned the GitHub link where I have added all this code and also the explanation that I am recording right now. So you can always go through the README of the GitHub repository and understand it from there also. And kind of I'm thinking of publishing a Medium vlog, but can't assure it. It needs to be approved. So yeah. So thank you everyone for joining. This is me, Victor Basu, and have a good day. Thank you.